Hello everyone, welcome to new class. Today's class is two variable Kmap. A two variable expression can have 2 raised to 2, that is 4 possible combinations of the input variables. Let the input variables be A and B, and each of the combinations, that is A bar, B bar, A bar, B, A, B bar and A, B. So these are the possible 4 combinations with the variables A and B. And each of these combinations are called minterm. And that is in the SOP form. SOP form, that is sum of product form. And instead of representing the minterms in terms of the input variables, using the shorthand notation, the minterms may be represented in terms of their decimal designations. That is, decimal designation are like M0 for A bar, B bar, and M1 for A bar, B, M2 for A, B bar, and M3 for A, B. And here assuming A is the MSB. The letter M stands for the minterm and the subscript represents the decimal designation of the minterm. The presence or absence of a minterm in the expression indicates that the output of the logic circuit assumes a logic 1. Logic 1 represents presence of the minterm and logic 0 represents the absence of minterm in the expression. For example, if we have the expression A bar B bar plus A B bar plus AB, then the minterm can be expressed as M0 plus M2, that is, this is 0 0 and this is 1 0, this is 1 1. So the minterm will be M0 plus M2 plus M3, that is sigma M0 2 3. And this is read as sum of minterms 0 2 3. And this can be expressed or indicated by a two variable Kmap. So let us study about the mapping of SOP expressions using the two variable Kmap. So a two variable Kmap has 2 raised to 2, that is 4 squares. And these squares are called cells. And each square on the Kmap represents a unique minterm. So these squares represents minterm. The minterm designations of the squares are like this. That is A and B here, and the values of A are represented in the column wise, that is 0 and 1. Here B, 0 and 1 are represented in the row wise, and these are the minterm designations, and it is 0 0. So we can write A bar B bar 0 1, that is A bar B, and 1 0, that is A B bar, and this cell is 1 1, that is A B. In this way we are representing the two variable Kmap, and this cell represents the decimal number 0, and this is 1, this is 2, and this is 3. So a 1 placed in any square indicates that the corresponding min term is included in the output expression. That is, if a 1 is placed in any square, that means the corresponding min term is included in the output expression. And if a 0 or no entry in any square indicates that the corresponding min term does not appear in the expression for output. Let us do the mapping of this expression, that is sigma m 0 to 3. So we can map this expression like this, that is, this is a two variable Kmap, and the variables are A and B. Here 0, 1, here also 0 and 1, and this square is 0. The value of this square is 1, then 2 and 3. So the min terms present are 0, 2, 3. That is, this is 0. So put a 1 here. That is, for present terms put a 1, and for absent terms put 0. Next term is 2. So put a 1 here. Next is 3. So here also put a 1. And the absent term is 1. So put a 0 here. So in this way we can map the expressions, that is the Boolean expressions we can map using the Kmap. Let us do another example. Map the expression a bar b plus a b bar. So from the given expression we can write the min terms. That is, min terms are a bar b, that is 0 1. 0 1 is m1, 1 0, that is m2, that is sigma m1 2. And the Kmap is 4 squares. Then the variables are a and b, and the values are 0 and 1. Here also 0 1. The squares values are 0 1 2 and 3, and the min terms present are 1 and 2. So 1 is this one, so put a 1 here. For the present terms put a 1 in the squares, and for the absent terms put 0. So this is the mapping of this expression, and this is the case for the SOP forms. Next is minimization of SOP expressions. To minimize a Boolean expression given in SOP form by using the Kmap, we have to look for the adjacent squares having ones, that is min terms adjacent to each other, and combine them to form larger squares to eliminate some variables. And two squares are said to be adjacent to each other if their min terms differ in only one variable. That is, if in this case this is m0 and this is m1, and this is A bar B bar, and this is A bar B. That is A bar B bar plus A bar B. So in this case, here the variable differ, that is differ only in B. That is B is different in these two cases and A bar is common. So they may be combined to form 2 square to eliminate the variable B. That is, we can combine these two squares to eliminate this variable B. That is, here this is A bar. So while combining these two squares, we will get the common, that is the same variable, and the different variable is get eliminated. So here the answer is A bar. And here M0 and M2 are adjacent to each other. So we can combine these two squares. And here this is A bar B bar plus, and this is A B bar. And here the variable different is A. So we can eliminate that variable, and the answer is B bar. And in this case, M1 and M3 are common, and we can combine that two squares, and this minterm is A bar B plus A B, and the variable different is A, so we can eliminate A, and the answer is B. Here also these two are adjacent. So two squares are said to be adjacent to each other if their minterms differ in only one variable. So here also we can write A B bar plus this is A, and here this is B. So here the variable different is B, so the answer is A. And here in this case all the minterms are 1. That is, two squares adjacent to each other can combine to form a 4 square. A 4 square eliminates two variables. That means here this is A bar B bar plus A bar B plus A B bar plus A B, and we get A bar plus A, and that is equal to 1. So if all the minterms are equal to 1, then we will get the answer as 1. That is, the two variables are eliminated, and a 4 square is called a quad. This is called quad. And to read the squares on the map after minimization, consider only those variables which remain constant throughout the square and ignore the variables which are varying. That is, in this case, A is constant, so consider that variable only and eliminate the variable which is differ. And in this case, this is M1 and this is M2, and these are not adjacent to each other, and its values are a bar. This is a bar b plus, and this is a b bar. So here they differ in more than one variable, and we cannot eliminate one variable here. So here this is the answer itself. So if the minterms are not adjacent to each other, we cannot eliminate variables. Let us do an example. Reduce the expression a bar b bar plus a bar b plus ab using mapping. So this is m0 and this is 0 1, that means m1, and this is ab, that is 1 1 m3. So the minterms are sigma m0 1 3, and we can draw the Kmap, that is variables are a and b, 0 1 0 1 0 1 2 3. So the minterms present are 0. Put a 1 here, then 1, put a 1 here, then 3. So put a 1 here, and this is 0. So these two squares are adjacent to each other, and we can combine these squares. So while combining these squares, we will get the answer a bar. So this is the constant term, and here b is changing, that is 0 and 1. So while combining these two adjacent squares, we get the answer as a bar. And here there is 1 in the fourth square. So combine these two squares. While combining these two squares, we will get the answer as this is b, and here a is changing. So the answer is plus b, because this is SOP expression. So we can write a bar plus b. So this is the reduced expression. And if we want to draw the logic diagram, it is OR gate. Inputs are a bar and b. Next is mapping of POS expressions. Each sum term in the standard POS expression is called a max term. A function in two variables has 2 raised to 2, that is 4 possible max terms, and that are a plus b, a plus b bar, a bar plus b, and a bar plus b bar. And they are represented as m0, m1, m2, and m3 respectively. Here the uppercase M stands for max term, and its subscript denote the decimal designation of that max term obtained by treating the non-complemented variable as a 0. Non-complemented variable is treated as 0, and the complemented variable as a 1. A two variable Kmap with max terms can be represented as like this, that is 0 1 0 1, and here this max term is a plus b. Here a plus b bar, because the non-complemented variable is treated as 0. So we can write a plus b for this 0 0, and for this 0 1 we can write a plus b bar, and here 1 0, that is 0 1 2 3, and this one we can write a bar plus b, and here a bar plus b bar. So for mapping a POS expression on the Kmap, zeros are placed in the squares corresponding to the max terms which are present in the expression, and ones or no entry. Ones or no entry are placed in the squares corresponding to the max terms which are not present, that is absent terms, which are not present in the expression. Let us do an example. Plot the expression a plus b into a bar plus b into a bar plus b bar on the Kmap. So from this given expression, we can write the max terms pi m. A plus b is 0, a bar plus b is 2, and a bar plus b bar is 3. So remember here in POS term, a is 0 and a bar is 1. So this is 0 0 0 1, and this is 1 1. And we can draw the Kmap, that is a b 0 1 0 1 0 1 2 and 3. So the max terms present are 0 2 3. So 0 is this square, so place a 0 there, because in POS term for the present terms put a 0 in the square. Next is 2, that is here 0, then 3, and for the absent terms put a 1. Next is minimization of POS expressions. To obtain the minimal expression in the POS form, map the given POS expression onto the Kmap and combine the adjacent zeros into as large squares as possible. And here, if the complemented variable in this row is a constant, that is here these two squares are 0 0, so we can combine these two squares and the answer will be a, that is here 0 means it is a, and here we can combine these two squares and its value is 1. 1 means here it is b bar, and here also we can combine these two squares and its value is 0. 0 means it is b, and here we can combine these two squares and its value is 1, that means it is a bar. And if all the squares are 0, then we can combine like this, and its value here is 0. So the variable which is changing is, we can eliminate that variable, and the variable which is constant throughout, we can write the variable as it is. So here b is changing, so we can write the variable a, and here also the changing variable is a, so we can eliminate a. So in this way we can do the minimization of POS expressions using Kmap. Let us do an example. Reduce the expression a plus b into a plus b bar into a bar plus b bar using mapping. So this is a POS expression, that is product of some terms. And we can write the max term, that is max term here is pi m. This is 0 0, that is 0, then 0 1, that is 1, and this is 1 1, that is 3. So the max terms are pi m, 0 1 and 3. And we can draw the K map. A B 0 1 0 1 0 1 2 3, and the max terms present are 0 1 3. So 0, then 1 and 3 are present, and 2 is not present, so we can put 1 here. So here we can combine these two squares and we get the answer as, the changing variable is b, so we can write a. And also we can combine these two squares. Here the changing variable is a, so we can write 1, that is b bar. So the answer is a b bar. And we can draw the logic diagram as a, and this is b bar. This is the output. So this is about the two variable Kmap. Thank you for watching the class. If you like the classes, please like, share with your friends and subscribe my channel.